Good morning. Welcome to another session of EE403 Distributed Generation and Smart Grids. In the last session we had seen intelligent electronic devices, and today we will see what is a PMU and WAMS. Before we proceed further, let us see a quote by Bruce Lee. Absorb what is useful, discard what is useless, and add what is specifically your own. We are going through the last part of the module 3, and we will finish module 3 today. So we start with Phasor measurement unit or PMU. They are digital data recording devices that measure and export GPS synchronized high sampling rate, typically 6 to 48 samples per cycle, dynamic measurements of phase, voltages, currents and frequencies. It can replace the traditional SCADA functionalities. These are two standalone PMUs by different companies, and these are two integrated PMUs from GE and SEL. Before going to PMU, let us understand the importance of phase angle measurements. What causes power to flow in the grid? In a DC power system, power flows from a point of high voltage to a point of low voltage. But in an AC power system, power flows from a point of high voltage angle to a point of low voltage angle. The higher the angle, the greater the power flow. So this is important. Now this shows the Phasor representation of a sinusoidal waveform. So a phasor can be represented by a rotating vector or phasor. You might have already studied these things in your first course in electrical engineering. And phasor measurement units use DFT to obtain the fundamental frequency components of voltage and current. Here you can see two PMUs located geographically far away. Sorry. So you can see this PMU at bus 1 and another PMU at bus 2. And both these PMUs are connected to GPS satellites. The red waveform and the blue waveform, they are the signals from the two PMUs. So the blue waveform is coming from PMU at bus 1, and the red waveform is coming from the PMU at bus 2. And the dotted line is the common reference signal obtained from the GPS. With this information, we can find the magnitudes of these voltages and also the phase angles θ1 and θ2. This is a comparison of SCADA and PMU. SCADA typically uses analog signals, whereas PMUs use digital signals. The resolution of SCADA is about 2 to 4 samples per second, whereas PMU it goes up to 100 samples per second. In SCADA, the observability is steady state, whereas in PMU we can have dynamic or transient observability. The monitoring we can do only local monitoring with SCADA, whereas by using PMUs we can have wide area monitoring, which we will see with WAMS. In SCADA we don't measure the phase angle, whereas in PMUs we get the phase angle measurement also. This is a comparison of SCADA and PMU. We can compare SCADA and PMU with an X-ray and an MRI. So you can see the data from an SCADA. The information comes every second with no time synchronization, whereas in a PMU the data we get every millisecond with time synchronization. So here we get a very detailed picture of the dynamic variations. This picture shows the data from a SCADA and a PMU. You can see a very short interval of time can be seen very clearly using a PMU data, and this will enable us to analyze the various problems and predict possible faults. SCADA measurements cannot see most oscillations, and the worst part is they can give misleading impressions. Synchrophasors are needed to observe oscillations because of faster data sampling, greater data resolution, and wide area. This is the block diagram of a phasor measurement unit. You can see the analog inputs coming to an anti-aliasing filter. From there it goes to an A to D converter, and then a phasor microprocessor and transmitted over modems. Also it receives GPS. From the GPS it receives the time and position information, which is fed to the A to D converter after phase locking. Let us understand the working principle of a PMU. The voltages and currents in their analog form are derived from the PT and CT secondaries, which are then fed to the anti-aliasing filter shown here. There will be a surge isolation section also, which is omitted in this block diagram. An anti-aliasing filter is used to restrict the bandwidth of the bandwidth of the signal to satisfy the Nyquist-Shannon sampling theorem for a fixed sampling frequency of the system. Now about the GPS. The GPS provides accurate information about the location and time of the GPS receiver's location. It consists of 24 satellites orbiting in 6 geosynchronous orbits, such that at any given instant 4 satellites are visible from any point on the Earth's surface. These satellites are capable of transmitting common access 1 pulse per second with an identifier, which is accurate about 1 microsecond at any location on Earth. This pulse combined with the time tag is crucial for the applications. Now coming to the phase lock oscillator, pulse signals from the satellite are phase locked with the sampling clock. The PLO divides the 1 pulse per second signal from GPS into the required number of pulses per second for sampling. when the phasors are time tagged, then we will refer to it as synchrophasors. Using the synchronized clocks as a reference, a PMU creates the phasor representation of a complex sinusoidal signal. All PMUs in the power system use the same time reference. The phase angle differences between the phasors are hence accurate. And then finally we have a to D converter, which converts analog signals to digital signals, and then it goes to a microprocessor connected to a modem, through which it can be transmitted to remotely located control center or cloud for computation purpose and analysis. The synchrophasor representation is shown here. You can see when the phase changes, the synchrophasor representation also changes. This is a conceptual diagram of a power system with PMUs connected at different locations. This is the basic principle of WAMS. You can see PMUs connected at 4 different locations, which provide phase information of voltages and currents at these 4 locations, and which are location and time stamped using GPS, and this information can be used for further processing, analyzing, etc. The advantages of PMU are we get more number of samples, 25 to 100 phasors per second. The signals are GPS time synchronized to control center from all locations. We get a finer view of the electrical system. We can employ adaptive protection system. Most importantly, a post disturbance analysis with more accuracy can be done, which helps in planning, and there are many more applications. The possible applications are oscillation detection, fault location identification, fault classification, event analysis, model validation, and situational awareness. Now moving to wide area measurement systems, abbreviated WAMS. It is a collective technology to monitor power system dynamics in real time, identify system stability, related weakness, and helps to design and implement countermeasures. Basically, it makes use of many PMUs connected at different locations, precisely time synchronized, and we get all the information of voltage and current phases and other quantities like frequency, rate of change of frequency, breaker positions, etc. This is a picture of WAMS where you can see large number of PMUs connected at various geographical locations far away. This is the system architecture of WAMS. You can see large number of PMUs, and the signal from these PMUs go to a data concentrators, and there are many data concentrators in a WAM, and the signals from these data concentrators are finally sent to a super data concentrator where it is processed and analyzed. The various components of WAMS, as we had already seen, one is the PMU, which is connected to a GPS clock to get the time and position stamping. And then there is a DULR, dual unit line relay, a PDC is a data concentrator, pulse data concentrator, and the communication infrastructure to pass on these signals to the central application. So these are the various components: PMUs, Phasor data concentrator, or abbreviated PDC, GPS for time synchronization, the communication channels. Then in the central control station there will be visualization and analysis tools, wide area situational awareness system, and wide area protection and control systems. This picture again shows the data coming from two different PMUs located at remote locations, and with the common signal we can find the phase differences between these two signals. We get the delta 1 and delta 2 information, which is the phase information, and we can hence find the difference between the phases also. So we make use of the absolute time reference across the power system, and that is the main advantage of WAMS. A circuit, a two-area 4-machine circuit is shown here. You can see the distance between G1, G2, G3 and G4. They are separated by geographically by large distances. The PMUs connected, you can see there are two PMUs connected, gives necessary signals from generator 2 and generator 4, and this signal can be used for controlling the damping or controlling the oscillations. These are the abbreviations used in this presentation, and these are some of the references used in this presentation. If you wish to contact me, please ring to this number or email me at this email ID. With that, I sign off. See you again with another session soon. Thank you very much.